What's up, guys? We're going to talk about return-oriented programming today. This is an extension of our buffer overflow attack, which we've done in the previous weeks. The video is on the comment section. This is going to be a little bit involving, so sit back, grab some bites, and yeah. Okay, so in our previous example, in our previous video, we had a program which opened a file, file.txt it was, and we read the first line. After reading the line, we copied the line to another buffer, and this is 160 bytes, and we printed out the line. Now we used strcpy, so strcpy is flawed. A buffer overflow can happen because we can feed it a buffer which is longer than 160, and it will just continue writing onto memory. In this case, it will be the stack. So let's have a little bit of a look at how this program works, just to rejuggle our memories. Over here we have our program and we have our file.txt. The first line of the file has the word short. So if we run this test, it will just read the first line and print it out. No issues so far because that is shorter than 160 bytes. Now, if we create a line that's longer, it's going to segmentation faults. Yeah, it's gonna crash. Yeah, so we know why. Okay, we've seen that in the previous video. Now what we did in the previous video was we took advantage of the return address, and since the return address is stored on the stack, we overflowed the buffer and we put a memory address. We put the address of this function, and as you can see, this function is not being called. So we put the address of this function in the file. So if we edit the file now here, this one here, this is the address of that function. Okay, so that's what we've done. So when writing this buffer, it will overwrite the return address, and instead of returning to here after completion of this function, because we've overwritten the return address to be this one, once this finishes, it will continue over here. And so when we run it, you can see that this gets executed, and you'll see a bunch of these. So in our previous example, we spoke about the fact that you've redirected control to another function in the executable, and that's not going to do much. So we spoke about system calls and, being able to run something else, and that's what we're going to do today. So there are a number of ways we can, basically we will be hijacking the whole machine. Okay, now let's say, for example, we've got a program control here, .cpp. All it does, it just displays the string host compromised. It's not the same as these, okay, it's different. So if I run that program now, yep, it just displays that string. So what we're going to do is we want to run this program. You can do it via a system call, and a system call is like saying there's a list of functions which are available, and you basically just send an instruction to the CPU and set the parameters via registers, and you just issue a service call. We're not going to take that approach. We're not going to use the system call. Instead, we're going to use the standard C library. We're going to use the standard C library to grab a function from there and run it. Now, the standard C library, you guys know, it's just available with every program, so it has all the basic functionality, like, writing to files, reading memory, etc., etc. Okay, so we're going to exploit some functionality. We're going to make use of some functionality in the libc library to our advantage. Now, in this library, there's a function called system, which takes a parameter, which is the part of the executable you want to run, and it will run it. Now, there's a number of issues here, but before we go forward, let's have a little look at how the stack works. So over here, we've got some workings, okay? This is a sample program. It's actually the control program. Let me see if I can scroll this over here. Here we are. So this function here, this program here, is being mapped over here. This is the stack of this program. Each function has its own stack frame, colored in a different color. And without going into too much detail here at this stage, just note that the larger addresses are at the top and the smaller addresses are at the bottom. And the stack grows downwards. So you've got the stack pointer here, pointing to this location. Let's say you've got R11 is not the stack pointer, okay? That's something else. We're not going to look at that. That's the previous return address, not even the prior one, the one before it. Let's not worry about that. Over here you got the stack pointer, and if you push a value onto the stack, what will happen is it will move the stack pointer 4 bytes down in this case, because we've got a 32-bit processor. It's an AMD processor running on a Raspberry Pi. It will move the stack pointer 1 byte down, and it will push whatever value you give it. So if you push 0, it will put 0. Oh, oops. That's 0. It will push 0 onto the stack. So we've got a pushed 0. If you pop a value from the stack, it will grab the value 0 in this case and pop it over onto the register that you choose, and then it will move the stack 4 bytes up. So yeah, you got this push pop going on. Okay, now that's a little bit about the stack. Now what happens when a function gets called? Let's pick this orange function here. Now we've got the previous return address, which is it's obtained from the R11 register, and you've also got the last return address. Okay, oops, I inverted them, sorry. So you've got the last return address first, and then you've got the previous return address. At some point later on, when the function reaches the close, it will set R11 to this value. Okay, we don't need to worry about that. We don't want to worry about that. So now over here, you've got the function parameters and the local variables. So in our case, in our test program, we actually got a much larger function. We need much more space because we've got this 160-byte buffer. So over here, in this case, if it were it would be much larger, yeah? So let's assume the buffer gets overflowed here. We write more, we start overwriting the local variables that are before the current variable, and then we get to the previous return address, we overwrite that, and we overwrite the last return address. And you can keep going, really, so you can essentially destroy the whole thing. Now, when this function exits, okay, when it's reaching the end, it wants to go back to here. So if we put the address of stack smash attack here, which is what we've done, it will go to that place and will continue. It will set the program counter register, which is the register which holds the current instruction. It will set it to the contents over here and continue from there. Now, so essentially that's what would happen. Now, if we have a problem, so what our objective is to continue on from what we were doing. Our objective is to run the system function in the libc library, and the system function takes one parameter. Now over here, if we just put the address of system here, so first of all there's a whole investigation on what and where will system be loaded. So there's a number of protections which have been introduced. One of them is ASLR. So ASLR defines the locations in memory where, when an executable is loaded, where things will be loaded in memory. It randomizes them if it's enabled, so that if you run the same program the second time, you won't have the same addresses. You won't be able to calculate the libc library once and have it right and run the same program again and have it the same. It won't be the same, and other things. So ASLR has been actually enabled in my system and I had to disable it. So yeah, there are other also protection mechanisms, like for example stack protection. Each frame here will have some, I believe it's one word which will act as a protector, so you can't overflow the buffer at all, ever. Now, well, let's not say that, okay? Because actually, yeah, we could probably still overflow it. I haven't done much investigation in this space yet, but essentially, yeah, that's what a stack protector's intention is, to avoid having someone overflow the buffer. If you've got a function, say memcopy, you can still overflow the buffer because memcopy doesn't stop copying when it reaches the 0 byte. So that's what I was trying to say before. So yeah, you can still, yeah. Now, in my system, stack protection actually wasn't enabled, and I don't think it is available, or it's not, for whatever reason, it's not enabled. Okay, I'm using a Raspberry Pi. So yeah, free tickets. Now, what's next? So essentially, if we put the system, let's assume we're here and we're going to overflow, we're going to override the LR, the last return, with system. That's all good, but system doesn't really work, because it needs a parameter and it needs to be on R0, and the parameter needs to be a valid string which points to a valid file which executes. So and we have no mechanism, well, we have actually, it's just the question, how are we going to get this program that's running, and we don't have access to its sources. How are we going to tell this program to, first of all, get the part of this control program, and secondly, run it? So, what we do, at the top of the stack for this current process, near the top, there is a pointer to all the environment variables. So if we create one environment variable with the whole path to the program, we might be able to find the address of that string. And that's what we've done. So if we look at our environment variable here, let's see. Here, can you guys see there's bcrop over here? That's our environment variable. If we run bcrop, oops, yeah, it will run my program. Yeah. So essentially we want to get the address of this over here. Anyway, there's a process to doing that, and yeah, we get it. We're not gonna get into too much detail, as otherwise we'll be here forever. But there are ways to do it, okay? And if you've got difficulties with getting it on the remote server, you might be able to get it by downloading the program that you're attacking. Let's say you know there's a vulnerability in SSH, and you know that SSH is running as root, but you don't have root access to the system, so you want to take advantage of that vulnerability. You download the SSH executable from the remote server, and you download it on a system which is similar to the host machine, and you will be able to do some investigation there. Right? So that's gathering information. Anyway, back to our problem now, because there's so many layers to this. So over here, what we're looking at now is something which doesn't work. If we put system call here, it doesn't work because it doesn't know what program to run. We found the address of the program. So, but how do we tell how do we tell the system? Because this needs to be an R0 register. How do we load this address once we find it into R0? And this is where a little bit of hacking gets in the way, because what we do is we use assembly and disassembly. We think a little bit. So what do we really need to do to get this address? We need to first have it in the stack, because that's the only way we can put it in the program. So we need to somehow put this address on the stack, which means write it on the file. And somehow from the stack we need to be able to put it on the R0 register. And we have this instruction pop0, which does that. Sorry, pop R0, which will grab a value from the stack, and it will also grab a value, and put it on R0. But then what do we do? How do we get that to run? So how do we run it? This stack is not executable, it's just addresses. We need something to run. We need it somewhere. So we can do so many things with this pop R0. Actually, you don't just do pop R0, we also do pop PC. So what you do is you actually store the address of the program, the address of the program, and of the string, and the address of the system function. So you have them following each other. So you first pop this one onto R0, and then you pop this one onto the program counter. That way you have the address of this program in R0 and the address of the system function. So then, the system in the program counter. And since the program counter is the current instruction, it will continue on from there. And that's how you run your executable. It's that simple, but it's not. Now, over here, you've got pop R0, pop PC. How are we going to get these two instructions to run at a particular point when you've got the stack pointing to those two addresses. Yeah? Easy. Well, yeah. You don't, you need to find somewhere where this exists. And you can look in your current executable. So what you do is over here, okay, let's take it a step backwards. Over here, oopsie, okay. Let's have a look at this bytecode thing that we've got. We've written this script that assembles and disassembles stuff. So I'm not assembling. Yeah, we're using some assemblers and disassemblers here. That's all we're doing. Nothing special. All right. So code. We're gonna do a pop. We're gonna pop. What was it? R0, and we're gonna pop also PC. That's it. That's all we need. There we go. So if we disassemble the program, you can see this instruction corresponds to this binary sequence, this word set of bytes, 4 bytes. Those 4 bytes, if we can find them anywhere in our executable or in any library that the executable loads, and in this case we can have a look at libc because that's a huge library, what we can do is we can say, well, okay, let's put the address of this pop R0 PC of this byte sequence over here. That way, the last return address will be the address of this pop. So it will then continue running from there, which means over here you will have the address of your program, and over here you will have the address of the system function. Now you also can keep going, all right? So you can keep going, and you might want to hide the segmentation fault error by redirecting the program somewhere else, or you can make it exit if you want, I don't know. But essentially what you want to really do is you want to get to run your program, because once you do, you have full control of the system, in this case at root level. You might set up some network socket to listen on some socket, and you can connect to it and do whatever you want, really. So you can do whatever you want. Whatever you want, you can write that control program to do whatever. So anyway, now over here, what we're doing is, yeah, we've done, we're mapping out our plan, right? So that's our plan. So we want to find this instruction inside libc. So anyway, we've done that, and we actually were not able to find this instruction. However, we found something similar. We found this instead. Isn't that the same? This is what we found. That's even better, actually. Yeah, no, that's cool. Doesn't matter, because you got to keep in mind that if you've got an address, if you've got an instruction with 0, 0, strcopy is going to stop copying there, and it will not keep writing this stuff. So if one of these addresses has 0, 0 in it, that's not going to be valid. So you got to keep that in mind. But in this case, no, in this case, it's on a separate byte. So that's cool. All right, so, but anyway, we found this instruction in our libc library. So all we had to do really is, well, we're going to demonstrate it here, I guess. All we had to do was, over here we store the address of the we call it gadget. Okay, it's called a gadget. This is called a gadget. The gadget. Over here you store the address of your control program. Over here you store the address of the system. Oopsie. Sorry, actually. Over here you actually store a dummy whatever, and over here you store the address of your system call. So what will happen is it will come here, it will overwrite, it will write this stuff onto the stack, and when the function finishes it will go here and it'll say, go to gadget. Okay, cool. Pop R0, which is the control program, pop R4, which is a dummy variable, and then pop system into the program counter, and system will pick up R0 and it will run our program. So I'm going to revert this back to the way it was, but basically I wanted to explain that. So yeah, so that's what we've done. So if we look at the file now, let me see if we can do some where was it? I think it was, yeah, we didn't run it. So okay, let's go back to this one here, host smash. All right, so over here if we open up the file now, file.txt, okay, we forgot to, okay, let's I'm sorry about that. So let's over here, this is our return oriented line, programming line. Okay, so if we delete this and we copy it over here, that's the first line. So if we have that line on the first, as the first line, the program's going to read it and it's going to redirect control to, yeah, like we said. Now there are so many other ways this can be done. There's like, even you can do what you can create escape codes and run a shell. There's a you can create, and like you can in our where was our, you can do this. I'll explain. Let's go back to this. Let's go back to bytecode, disassembly. You can also do this, E11 80 BD E8. So you can write these directly in the file and they will be executed, but yeah, we didn't invest too much time on that approach. Okay, so it's doable. There are different ways this can be done. So this is just one way. Okay, so anyway, off topic. Let's continue because we're taking a lot of time now. So over here, I want to show you guys how this will look. File.txt. Okay. So this is the first. This is the first line. Okay. Now, if we come somewhere here, wherever it is. Okay. This is the end of the line. Now, as you can see, there's more now. There should be 4 addresses. Yeah. We had in here, over here, we had. Oopsie. We didn't undo that. 1, 2, 3, 4. Yeah. Okay. Now, so that's 1. Actually, we're gonna start writing. We're writing the buffer, right? We're writing the buffer, and it starts overwriting from here. So it starts writing. Okay, let's go back. 1, 2, 3. Oopsie. There. That's it. Now, So this would be the gadget, yeah, 76EA DBB8, and this is in the libc library. So we actually hacked into the libc library to find our byte sequence. And there are tools to actually help you do that as well. So those the first 4 bytes, 1, 2, 3, 4, and then there's the control, the part of the program, yeah, and then there's the dummy variable, yeah, this one here, dead beef. And then we oh, yeah, don't forget you got to take into account byte ordering as well. Now over here we've got the address of the system function, which is also in libc. So we are going twice to libc here. We're going once for the gadget and once for the system call. Anyway, so if we run the program /test now, as you can see, it started printing out the line, but then it redirected control into host compromised. Yeah, now this segmentation fault could be hidden, okay, if we keep doing other things. Basically, that's the whole point of return-oriented programming. You are programming by making use of the return values over here. So it's a pretty powerful technique, and yeah, I hope you enjoyed this video. Feel free to comment, and yeah, thank you for watching.